So we're going to recap Stokes' theorems one more time. And when I say Stokes' theorems, plural, what I really have in mind are four different results. The first one in vector analysis that we encountered was the fundamental theorem of line integrals. The second one that we encountered in the order that we were doing things was the was Green's theorem. Green's theorem was a way of turning a circulation integral in the xy plane into a double integral in the xy plane instead. We're going to see later on today how Green's theorem was just a special case of what happens in 3 dimensions if we can turn a circulation integral into a surface integral, and that theorem is called Stokes' theorem. And then the last theorem was the one that we met a couple of days ago, the divergence theorem, which can turn a surface integral on a closed surface into a triple integral on the region bounded by that closed surface. So in a minute, I'm going to go back to that diagram that sort of strings everything together. And every time I put that diagram on the screen, I feel like this is me. Like, you know, line integrals over here, flux integrals over there. Stokes' theorem is this way. If you're a closed surface, you go down that way. So yeah, fortunately or unfortunately, we're going to take a look at that one more time, just to make sure that our context is clear. That if I'm computing a line integral, then on the one hand, if my vector field is a gradient vector field, so if my vector field is what is called an exact form, so I'm going to drop those couple words in here and not explain really the generality of what it means, but if my vector field is an exact form, if it's equal to the gradient of some scalar function, then that integral is going to be path independent, and all we have to do is take an ungradient to find the scalar potential function, evaluate it at the endpoint, evaluate it at the beginning point, and subtract. We call that the fundamental theorem for line integrals because of its close resemblance to the fundamental theorem of calculus in single variable calculus. And in fact, all 4 of these theorems, I call them all Stokes theorems because they all follow from the most general version of Stokes theorem that you learn if you go a little bit more sophisticated mathematically. There's a single theorem in geometry called Stokes theorem that the fundamental theorem of calculus, the ordinary one, is a special case of. This version of the fundamental theorem of calculus is also a special case of it, and so is Green's theorem, and so is the divergence theorem, and so is the theorem that most vector calculus textbooks refer to as Stokes theorem. So it's all part of the same, it all falls out of the same theorem ultimately at the end of the day. But anyway, if we have an exact form in a line integral, then we have a path-independent integral, and all we have to do is find that potential function and measure its difference from ending point to starting point. If I'm computing a flux integral, then that vector field can be an exact form in a different way. It can be equal to the curl of something. And if my vector field is equal to the curl of something, then I can use Stokes' theorem to convert that flux integral into a line integral. And in that case, it would be the line integral of whatever is this vector potential function, which I call b down here. So it would be the line integral of b. It would be the same as the flux integral of the curl of b, if you like. So that's sort of the exactness case for a flux integral, is it sort of takes us into Stokes' theorem and through Stokes' theorem back to a line integral instead. On the other hand, both of these computations have special cases when our region of integration is a closed region. So if I take a line integral around a closed curve, it's called a circulation integral, then that line integral can be converted into a surface integral using either Green's theorem if my curve lives in the xy plane, or Stokes' theorem, which we're going to get more practice with today, if my curve lives in 3 dimensions. On the other hand, if I'm doing a flux integral in 3 dimensions through a surface that is a closed surface, so a surface which bounds all of 3 space into an inside and an outside, and we can't get from one to the other without crossing through my surface, then we can convert that flux integral into a triple integral instead. And that triple integral then, according to the divergence theorem, is the triple integral of the divergence in the region that's bounded by that surface. So just a couple of sort of graphics to sort of reconfirm what it is that's sort of actually happening here. So if I start with a curve that lives in the xy plane, then a curve that lives in the xy plane, which is a closed curve, I can find the circulation around that closed curve just by filling in that region and applying Green's theorem. So this is Green's theorem, that instead of finding the circulation around the boundary of this region in the xy plane, I can find the double integral of the scalar curl of the vector field inside of that region, because the scalar curl gives me the circulation density. So that's Green's theorem. What we're going to see today is that if instead of in 2 dimensions, my curve resides in 3-dimensional space, and it doesn't have to reside in a flat plane, even though this example looks like it does, then instead of filling in that, well, I guess one option would be to fill in that region as a filled-in region inside the xy plane, right, the way that we did with Green's theorem. And if I do that, I'm just going to get the same idea as before. But where the connection is going to come in today is that if I fill this in with a flat region in the xy plane, then all of my normal vectors to that region, which describe for me the positive orientation of the flux through this surface in the xy plane, are pointing upwards in the positive z direction. And so it turns out that if I were to take the vector curl of a vector field living in the xy plane and dot that vector curl with a normal vector that points directly in the z direction, that's going to spit back out Green's theorem scalar curl formula for me. The dot product of the vector curl with a vector that points only in the z direction is just the scalar curl of that vector field in the xy plane. But the beauty of Stokes' theorem is we don't have to fill in our curve with a patch of surface in a particular way. We can fill it in any way that we like. So I could use this surface instead and compute the surface integral of the vector curl through this surface if it's more convenient for me. And there's a whole bunch of different surfaces that all have the same boundary. They're all of them going to have the same surface integral for this, because that surface integral is just equal to the circulation of that vector field around the boundary, according to Stokes' theorem. So this is the beauty of Stokes' theorem today, is that you have a single bounding curve that we're interested in the circulation around, but we can pick any surface of which that is a boundary, and the surface integral of the vector curl of the vector field through that surface is going to be the same. It's going to be equal to the circulation of that vector field around the boundary. And the third one of our theorems tells me that if I have a closed surface inside of three-dimensional space, so it divides space into an inside and an outside, and if I'm interested in the flux of a vector field through that closed surface, then instead of computing this flux integral as a surface integral, I can instead just sort of peel that orange and compute the triple integral of the divergence of the vector field on the region inside, the bounded region that's described by the interior of my surface. So surface integral through this surface, if it's a closed surface, is the same thing as the triple integral of the divergence of my vector field on the solid region bounded by that surface. So those are our three Stokes theorems, and this is how they all fit together.